All of modern physics is built on the foundation of general relativity and quantum mechanics. General relativity describes the big and how gravity is the curving of space-time caused by mass and energy, like how a ball in a blanket makes another ball circle around it. Quantum mechanics describes the very small, like elementary particles that make up everything, and force-carrying particles that are exchanged like a game of catch to produce interactions. But thanks to this evil equation, we can never know everything for sure, making the quantum world probabilistic and jittery. But this makes gravity very different from the other forces, and trying to put them together is a bit like putting me in a party. Everything falls apart. But we need both theories to understand extreme cases like black holes and the early universe. This is the quantum gravity puzzle, with the missing piece being the graviton, gravity's force carrier, and string theory might be our best solution. Instead of conventional points, string theory says all particles are formed by tiny filaments of energy that vibrate like violin strings, but instead of notes, they make particles. But what does this have to do with the graviton? Well, though we've never observed a graviton, we can still predict its features by looking at how gravity behaves. And one of the vibrations that string theory naturally requires matches our predictions, completing the puzzle and bringing gravity in line with the other forces, and is on a path to unify them. But string theory needs 9 spatial dimensions, as if 3 weren't enough. To understand how this works, take this rope for example. If I stood on it, I can only move in 1 dimension, along the rope. But there is another smaller dimension around the rope that only something small like an ant can move in. Similarly, in string theory, the 6 extra dimensions are curled into shapes called manifolds all around us, but are so small we can't experience them. But strings can. And like how a saxophone and trumpet make air vibrate differently because of their shape, the manifold's configuration determines how strings can vibrate, and vibration is key in string theory. This means the correct manifold might be able to explain everything, from the mass of a photon to the charge of an electron. But it'll be hard to find since only one out of a whole landscape of manifolds matches our universe. The rest might describe their own universes. So far, string theory promises to solve quantum gravity, explain the fundamentals of our universe, and even a whole multiverse, making it seem as perfect as ice cream, but it's actually far from that. Currently, we don't have a string theory. Instead, we have 5 versions that are all connected like a web, and trying to find M theory, the generalized string theory, but we hardly know much about it. And experimentally, string theory lacks evidence. There's no proof of extra dimensions, and the theory relies on supersymmetry, where each particle has a counterpart, but we've never seen any. But better particle accelerators might change this, or even find particles escaping to other dimensions. It's hard to test, but not impossible. And this means string theory may not be able to answer many questions yet, but as technology and research advance, it might explain the very nature of our universe, and that's worth waiting for.